Exploring the cosmos is not just a journey outward, but a voyage into understanding the very nature of existence. Unknown astronomer. Introduction: the grand design of the universe. The universe is vast beyond imagination, a cosmic tapestry woven from the threads of time, matter, and energy. Every point of light we see in the night sky is a reminder of our small yet meaningful place in this grand design. As we stand on the surface of a small planet orbiting an average star, we can look out and wonder at the immensity before us, a seemingly infinite expanse filled with untold mysteries, a celestial ocean stretching far beyond the reach of our senses. Our journey begins not in the present, where galaxies majestically swirl and stars blaze in the heavens, but in the depths of time itself, before the stars, planets, and even galaxies existed. We must venture back to a moment when everything we know, and everything that will ever be, was contained within an infinitesimally small, dense point. This point, a singularity, was the universe in its most primal form, a cosmic seed that held within it the potential for all matter, energy, and life that would later emerge. This moment of staggering simplicity, in which time itself had not yet unfurled its arrow and space had no meaning, was followed by an explosion of unimaginable complexity, a transformation known as the Big Bang. This event was not an explosion in the traditional sense, with material flying out into pre-existing space, but rather the birth of space and time itself. It was the moment when the universe expanded from that singularity, setting the stage for the cosmic evolution that continues to this day. But what is the universe? It is more than just the vastness of space and the celestial objects that inhabit it. The universe is the sum total of all that exists: stars, planets, galaxies, light, dark matter, and the very fabric of spacetime. Every particle, every force, every phenomenon we observe, is part of this grand cosmic whole. From the smallest subatomic particle to the largest galaxy cluster, all things are interconnected, part of a dynamic and evolving entity that is in constant flux. The universe is not static, it is alive with movement and change. Galaxies drift apart, stars are born and die, black holes consume and distort the fabric of spacetime, and dark energy drives the expansion of the cosmos ever outward. In this grand, ever-changing arena, we find ourselves on a small planet in a relatively unremarkable galaxy, yet our understanding of the universe places us at the very edge of knowledge, at the frontier of discovery. In our quest to understand the universe, we come closer to understanding ourselves. For millennia, humans have gazed at the stars and asked the same timeless questions: where did we come from? Why are we here? What is our purpose in this vast, seemingly indifferent cosmos? These are not just scientific questions, they are deeply existential and philosophical. As we peel back the layers of the universe's mysteries, we find that the answers we seek about the cosmos are also answers about our own existence. Are we alone in this grand cosmic expanse? This question, perhaps the most poignant of all, strikes at the heart of our curiosity and our sense of isolation. In the infinite sea of stars and galaxies, does life thrive elsewhere, or is Earth the lone island of life in an otherwise barren universe? The search for extraterrestrial intelligence, the study of distant planets, and the exploration of the conditions necessary for life are all part of our larger quest to understand not only the universe but our place within it. The beauty of the universe lies not only in its vastness but in its capacity to inspire wonder. As we delve into the mysteries of the cosmos, we are reminded of our own limitations, but also of our potential. We are the universe, contemplating itself. Our minds, the product of billions of years of cosmic evolution, are capable of probing the very origins of existence and imagining futures yet unseen. To begin answering these profound questions, we must first delve into the origins of the cosmos itself, into the very moment when time and space began their journey, a journey that has led to stars, galaxies, and ultimately, to us. The Big Bang, the birth of everything. The story of the universe begins approximately 13.8 billion years ago, with an event that forever changed the nature of reality, the Big Bang. Despite its name, the term Big Bang might conjure misleading images of a colossal explosion, as if matter erupted into an empty void. The reality was far more subtle, yet infinitely more profound. The Big Bang was not an explosion within space, it was the sudden and rapid expansion of space itself, a moment in which time, matter, and energy were born from a singular point of infinite density, a singularity. In that instant, the universe came into being, and the fabric of reality, as we know it, began to unfold. In the incomprehensible heat and density of those earliest moments, the universe was a chaotic, seething sea of pure energy. Space-time itself was expanding, stretching at a rate far beyond anything we can imagine today. In that primordial era, before even the most elementary particles existed, the laws of physics as we understand them did not yet apply. The universe was governed by a single, unified force, one that would later split into the four fundamental forces that govern our reality: gravity, electromagnetism, and the strong and weak nuclear forces. During the first infinitesimal fraction of a second, the universe underwent a process known as cosmic inflation. This rapid expansion stretched spacetime itself, smoothing out any irregularities and setting the stage for the more gradual expansion that continues to this day. Inflation was a brief but critical phase, lasting less than a trillionth of a second, yet it was responsible for the large-scale structure of the universe, the galaxies, clusters, and cosmic filaments that we observe across the cosmos. As the universe expanded and cooled, the energy from the Big Bang began to coalesce into matter. This marked the birth of the fundamental building blocks of the universe, subatomic particles. Within the first second, quarks and gluons, the constituents of protons and neutrons, began to form. These particles, which had previously been free to move independently in the extreme heat, now started to combine under the influence of the strong nuclear force, giving rise to the protons and neutrons that would later form the nuclei of atoms. But even then, the universe was still a hot, dense plasma, with particles moving too energetically to bind into stable structures. Over the next few minutes, as the universe cooled further, nuclear fusion began to take place. Protons and neutrons collided and fused to form the nuclei of the lightest elements, primarily hydrogen and helium. This process, known as Big Bang nucleosynthesis, laid the foundation for all matter in the universe. Yet, despite the creation of these atomic nuclei, the universe remained a dark and formless void. It would take hundreds of thousands of years before conditions were cool enough for these nuclei to capture electrons and form neutral atoms. This period, known as the recombination era, marked the first moment when light could travel freely through space. Before recombination, the universe was opaque, with photons constantly scattering off the free electrons in the plasma. But as electrons became bound to nuclei, the universe became transparent, and the first light, what we now observe as the cosmic microwave background radiation, was released, providing us with a snapshot of the universe as it appeared just 380,000 years after the Big Bang. At this stage, the universe was still a dark, formless expanse, dominated by hydrogen and helium gas. There were no stars, no galaxies, and no planets, just a vast, swirling cloud of primordial gases, slowly cooling and expanding. This era, sometimes referred to as the Cosmic Dark Ages, lasted for several 100 million years. During this time, gravity began to pull together clumps of gas, forming the first gravitational wells. Within these wells, matter continued to accumulate, growing denser and hotter, until, finally, the first stars ignited, marking the end of the Dark Ages and the dawn of the cosmic dawn. These early stars were unlike any stars that exist today. Composed almost entirely of hydrogen and helium, they were massive, burning hot and fast, and dying in spectacular supernova explosions. Their violent deaths scattered heavier elements into space, elements that would later be incorporated into new generations of stars and, eventually, into planets and life itself. These early stars also helped to reionize the universe, stripping electrons from atoms once more and making the universe transparent to light once again. As these first stars formed, they began to cluster together under the influence of gravity, forming the earliest galaxies. These galaxies, in turn, formed clusters and superclusters, connected by vast filaments of dark matter, which acted as a cosmic scaffold, shaping the large-scale structure of the universe. Over billions of years, these galaxies would evolve, collide, and merge, giving rise to the vast, complex universe we see today. Thus, the Big Bang set in motion a cosmic story, a story of matter and energy, of light and darkness, of birth, death, and rebirth. It was the moment when the universe transitioned from the simple to the complex, from the singularity to the grand cosmic tapestry. And though it is a story that began nearly 14 billion years ago, it is a story that continues to unfold, with each star that is born, each galaxy that forms, and each new discovery we make. We are part of this cosmic story. The very atoms in our bodies were forged in the hearts of ancient stars, scattered across the universe in supernova explosions, and eventually coalesced into the matter that would form Earth and all the life it supports. In a very real sense, we are the universe made conscious, the means by which the cosmos can contemplate itself. The Big Bang was not just the birth of the universe, it was the birth of everything: space, time, matter, and energy, and ultimately, the birth of us. As we look out into the night sky, we are looking back in time, seeing the afterglow of that moment of creation. And as we strive to understand the universe, we are striving to understand ourselves and our place in the grand cosmic story. The expansion of space and time. The universe has been expanding ever since that initial moment of creation, a fact that forever altered our understanding of the cosmos. The fabric of space-time itself is stretching, carrying galaxies along with it like leaves drifting apart on the surface of an inflating balloon. This concept, while seemingly abstract, is one of the most fundamental aspects of modern cosmology and has profound implications for our understanding of the past, present, and future of the universe. The idea of an expanding universe was first confirmed by the groundbreaking work of astronomer Edwin Hubble in the 1920s. By observing distant galaxies, Hubble discovered that they were all moving away from us, and that the farther a galaxy was, the faster it seemed to be receding. This relationship between distance and velocity is now known as Hubble's law, and it provided the first strong evidence that the universe was not static, as many had previously believed, but dynamic and expanding. It was as though space itself was growing, stretching the distances between galaxies. Hubble's discovery fundamentally changed the way we perceive the cosmos. If galaxies are moving away from us, it means that, in the past, they were closer together. In fact, if we rewind time far enough, about 13.8 billion years, we reach a moment when all matter and energy were concentrated in a single, infinitely dense point, the Big Bang. From that moment onward, space has been expanding, with galaxies moving apart as the universe continues to grow. But how exactly does this expansion occur? One way to think about it is that space itself is not something that exists within the universe, rather, it is the universe. Space-time is the fabric of reality, and the galaxies are embedded within it. As this fabric stretches, the galaxies move apart, not because they are flying through space, but because the space between them is expanding. This is a key distinction. The expansion of the universe is not like an explosion sending debris flying through pre-existing space, it's the space itself that's growing. A critical consequence of this expansion is its effect on light. As space stretches, it also stretches the light waves that travel through it. This process, known as cosmological redshift, causes the wavelength of light to elongate, shifting it toward the red end of the spectrum. The greater the distance a galaxy is from us, the more its light is redshifted, indicating that it is moving away at a faster speed. This redshift is one of the primary tools astronomers use to measure the rate of expansion and the distances to faraway galaxies. The discovery of the universe's expansion led to a cascade of questions about the nature of reality. One of the most pressing is, what will be the ultimate fate of the universe? Will it continue to expand forever, or will it one day stop, reverse course, and collapse in on itself? For much of the 20th century, cosmologists debated whether the universe would expand indefinitely or eventually succumb to the pull of its own gravity. If the amount of matter in the universe were sufficient, its gravitational pull might slow down the expansion and, eventually, cause it to halt. This scenario, known as the Big Crunch, envisions a future where the universe reverses its expansion, with galaxies accelerating toward each other, stars colliding, and matter being compressed back into a singularity, much like the state in which the universe began. However, recent discoveries have radically changed this picture. In the 1990s, observations of distant supernovae revealed that the expansion of the universe is not slowing down, as had been expected, but is actually accelerating. This was a shocking revelation that implied the existence of a mysterious force that opposes gravity, something that pushes galaxies apart at ever-increasing speeds. This force is now known as dark energy. Dark energy, though it remains poorly understood, is thought to make up about 70% of the total energy content of the universe. Unlike gravity, which pulls matter together, dark energy seems to have a repulsive effect on spacetime, driving the expansion of the universe faster and faster. The nature of dark energy is one of the biggest mysteries in modern physics. Is it a property of space itself, as suggested by Einstein's cosmological constant, or is it something even stranger, a manifestation of a new, unknown force or field? If dark energy continues to dominate the universe, its ultimate fate could be very different from the Big Crunch. Instead, we may be heading toward a future known as the Big Freeze. In this scenario, the universe will continue to expand indefinitely, with galaxies moving farther and farther apart. Over billions of years, the stars in these galaxies will burn out, leaving behind only cold, dark remnants. As the universe expands, it will become increasingly cold and empty, with even fundamental particles eventually decaying. In this distant future, all that will remain will be a vast, dark, and cold expanse, an eternal, frozen silence. Some more speculative theories suggest even more. It will not only push galaxies apart, but tear apart stars, planets, and eventually, the very atoms that make up matter. In this scenario, the fabric of space-time itself would be torn asunder, and the universe would end in a final, catastrophic disintegration. Other possibilities include the idea that dark energy could change over time. If dark energy were to weaken, the expansion of the universe might slow down and eventually stabilize, leading to a more balanced and static future. Alternatively, dark energy could increase in strength, accelerating the expansion to a point where even the laws of physics as we know them no longer apply. At this point, the future of the universe remains an open question, one that hinges on the nature of dark energy and the interplay between cosmic forces we are only beginning to understand. What we do know is that the universe is not static, and it never has been. From the moment of the Big Bang to the present day, the universe has been in a state of perpetual change. It expands, evolves, and will continue to do so for eons to come. In this ever-expanding cosmos, we find ourselves on a small planet orbiting a modest star, yet our ability to measure and contemplate these vast scales is a testament to the power of human curiosity. The expansion of space and time reminds us that the universe is far greater than we can ever fully comprehend, but it also invites us to keep exploring, to keep asking questions, and to remain in awe of the cosmic forces that shape our existence. Galaxies, islands in the cosmic ocean. Galaxies are the fundamental building blocks of the universe, each one a sprawling collection of stars, gas, dust, and dark matter, held together by the invisible force of gravity. These magnificent structures are like islands in a vast cosmic ocean, scattered across the universe in seemingly endless numbers. Current estimates suggest that there are hundreds of billions of galaxies in the observable universe, each home to millions or even trillions of stars, planets, and countless other celestial bodies. The scale of these cosmic formations is mind-boggling, with distances between galaxies stretching millions of light-years, a reminder of the sheer immensity of the cosmos. Our own galaxy, the Milky Way, is a grand spiral, a cosmic whirlpool swirling with stars, gas, and dust. With its sweeping arms curving out from a bright central bulge, the Milky Way spans roughly 100,000 light-years in diameter, making it one of the larger galaxies in the universe. It is home to more than 100 billion stars, including our Sun, and its structure is dominated by vast clouds of interstellar gas and dust, which are the birthplaces of new stars. Yet, for all its grandeur, the Milky Way is just one of billions, an island among islands in the cosmic ocean. Galaxies come in an astonishing variety of shapes and sizes, each one unique in its form and behavior. Some, like the Milky Way and its neighbor, the Andromeda Galaxy, are spirals, characterized by their pinwheel-like arms, which contain young, bright stars and regions of intense star formation. These spirals are the most visually striking of galaxies, their beautiful shapes carved out by the interplay of gravity, star formation, and the dynamics of interstellar gas. Within their spiral arms, nebulae, vast clouds of gas and dust, serve as stellar nurseries, where new stars are born from the collapse of gas under gravity. Other galaxies, such as elliptical galaxies, take on a more spherical or elongated shape. They are often older, with little gas or dust left for new star formation. These galaxies are typically populated by older, redder stars that have long since exhausted much of their hydrogen fuel. Elliptical galaxies can range in size from small dwarf galaxies to massive giants containing trillions of stars. They are less visually dramatic than their spiral counterparts, often appearing as smooth, featureless ellipses in the night sky. Then there are irregular galaxies, which defy the neat classifications of spirals and ellipticals. These galaxies are chaotic and disordered, often the result of gravitational interactions with other galaxies or internal disruptions caused by supernovae and starburst activity. They can be rich in gas and dust, sometimes forming stars at an astonishing rate, but their lack of structure makes them appear like cosmic accidents, a reminder that the universe is not always orderly. Despite their diversity, all galaxies are governed by the same fundamental forces of nature: gravity, electromagnetism, and nuclear fusion. At their hearts, most galaxies, including our Milky Way, harbor supermassive black holes, objects so dense that not even light can escape their gravitational pull. These cosmic giants, millions or even billions of times the mass of our Sun, play a crucial role in shaping the galaxies around them. The gravitational influence of these black holes helps to regulate star formation by affecting the motion of gas and stars near the galactic center. In some galaxies, particularly in the early universe, these supermassive black holes drive quasars, the brightest and most energetic objects in the cosmos. Quasars are powered by material falling into the black hole, which heats up as it spirals inward, releasing vast amounts of radiation. These beacons of energy can outshine entire galaxies and serve as markers of distant regions of the universe, allowing astronomers to peer back into the early stages of cosmic evolution. Yet, galaxies are not isolated islands, they are part of even larger structures, connected in a grand cosmic web. Galaxy groups consist of a few galaxies bound together by gravity, while galaxy clusters can contain hundreds or even thousands of galaxies. These clusters, in turn, form superclusters, which are the largest coherent structures in the universe, stretching across hundreds of millions of light-years. Our Milky Way is part of the local group, a small galaxy group that also includes the Andromeda Galaxy and dozens of smaller galaxies. This local group, in turn, is part of the Virgo supercluster, which itself is a component of the larger Laniakea supercluster. These immense structures are connected by vast filaments of dark matter, forming a web-like structure that spans the observable universe. Dark matter, though invisible to our eyes and undetectable by traditional means, exerts a powerful gravitational influence. It binds galaxies together and shapes the large-scale structure of the universe, providing the scaffolding upon which galaxies, clusters, and superclusters are built. Without dark matter, the gravitational pull of visible matter alone would not be enough to hold galaxies together or to form the cosmic web. The galaxies, while seemingly scattered at random, are intricately connected in this cosmic web. Between these filaments lie vast voids, regions of space where few galaxies exist. These voids can stretch for hundreds of millions of light-years and serve as a stark contrast to the dense clusters of galaxies found along the cosmic filaments. The distribution of galaxies throughout the universe, with dense regions of clusters and empty voids in between, resembles a sponge-like or foam-like structure when viewed on the largest scales. In this grand cosmic tapestry, galaxies evolve over billions of years, shaped by the forces of gravity, dark matter, and their interactions with one another. Galaxy collisions are a common occurrence in the universe, and when galaxies collide, they can merge to form a single, larger galaxy. This process often triggers bursts of star formation, as the gas and dust in the colliding galaxies are compressed, igniting the birth of new stars. Our own Milky Way is on a collision course with the Andromeda Galaxy, a meeting that will occur in about 4.5 billion years. When these two galaxies merge, they will form a new, larger elliptical galaxy, radically altering the night sky as we know it. In this ever-changing cosmic landscape, galaxies serve as the cradles of stars, planets, and life itself. From their brilliant cores to their spiral arms, from the supermassive black holes at their hearts to the quiet outskirts where stars like our Sun reside, galaxies are the homes of countless worlds, each one a potential harbor for life. They are the arenas in which the drama of cosmic evolution plays out, and in them, we find the seeds of our own existence. The study of galaxies is not just the study of distant objects in space, it is the study of the universe's grand design and our place within it. As we look out into the universe, the galaxies we see are not just points of light in the darkness, they are islands in a vast ocean of space and time, each one a beacon of cosmic evolution, each one a story waiting to be told. Stars, from formation to destruction. Stars are the furnaces of the cosmos, the celestial engines where the fundamental alchemy of the universe takes place. Through the process of nuclear fusion, they transform hydrogen into helium, releasing vast amounts of energy in the form of light and heat. These radiant beacons are the lifeblood of galaxies, providing the energy needed for planets to form, for climates to stabilize, and for life to potentially arise. Yet, despite their grandeur, stars are not eternal. They are born, live through stages of intense activity, and eventually perish, all according to their initial mass. This life cycle, though it may span billions of years, is a cosmic dance of creation and destruction, played out on the grandest of scales. The life of a star begins in the cold, quiet depths of a nebula, a vast cloud of gas and dust spread across the vacuum of space. Nebulae are often considered the nurseries of the cosmos, places where new stars are born from the remnants of earlier generations of stars. These clouds are primarily composed of hydrogen, the most abundant element in the universe, as well as trace amounts of heavier elements. Gravity, the invisible hand of cosmic creation, begins to act on the matter in the nebula, pulling the gas and dust inward. Over time, as more material accumulates, the cloud begins to collapse under its own weight. As the gas collapses, it heats up, and the region at the center becomes increasingly dense and hot. This process can take millions of years, but eventually, the core temperature reaches a critical threshold, about 10 million degrees Celsius. At this point, nuclear fusion ignites, and a star is born. Hydrogen atoms, the building blocks of the star, begin to fuse into helium, releasing an enormous amount of energy in the form of light and heat. This energy radiates outward, counteracting the force of gravity and stabilizing the star. The star has now entered the main sequence, the longest and most stable phase of its life. Stars like our Sun spend the majority of their lives in this main sequence phase, steadily converting hydrogen into helium in their cores. The balance between gravity pulling inward and nuclear fusion pushing outward keeps the star stable. For a star of the Sun's mass, this phase can last for billions of years. Throughout this time, the star shines brightly, providing energy to any planets that may orbit it. For stars like the Sun, this fusion process is relatively gentle, and they burn their fuel at a steady rate. However, even stars as enduring as the Sun have a finite lifespan. Eventually, after about 10 billion years, the Sun will exhaust the hydrogen fuel in its core. When this happens, the delicate balance between pressure and gravity will collapse. The core will contract, heating up even more, while the outer layers of the star will expand dramatically, turning the Sun into a red giant. During this phase, the Sun will swell to many times its current size, possibly engulfing the inner planets, including Earth. This transformation will make the Sun appear as a bloated, cooler, but much larger star. As a red giant, the Sun will begin to fuse helium into heavier elements like carbon and oxygen. This phase of stellar life is much shorter than the main sequence, lasting only a few 100 million years. Eventually, the Sun will shed its outer layers, creating a beautiful, glowing planetary nebula. What remains at the center will be the hot, dense core of the star, now a white dwarf. This remnant will no longer undergo fusion. Instead, it will slowly cool and fade over billions of years, eventually becoming a black dwarf, a cold, inert object that no longer emits light. For more massive stars, the end is even more dramatic. These stars live much shorter, more intense lives, burning through their hydrogen fuel in just a few million years. When the hydrogen in their core runs out, they don't just swell into red giants, they undergo a series of increasingly violent fusion reactions, creating heavier and heavier elements. These stars can fuse elements all the way up to iron, which is the most stable element in the universe. But when a star's core is made of iron, fusion can no longer release energy. Instead, it requires energy. At this point, the core of the star collapses under its own gravity, triggering a supernova, one of the most violent events in the universe. A supernova explosion releases more energy in a few seconds than the Sun will emit over its entire lifetime. The outer layers of the star are blasted into space, where they will enrich the surrounding nebula with heavier elements, which can then go on to form new stars and planets. This is how elements like carbon, oxygen, and even the gold in your jewelry are created, inside the hearts of dying stars, then scattered across the cosmos by supernovae. The fate of the star's core, however, depends on its mass. For stars with a core remaining after the supernova of about 1.4 times the mass of the Sun, the core will collapse into a neutron star. Neutron stars are incredibly dense, so dense that a sugar cube-sized amount of neutron star material would weigh as much as a mountain. These remnants are often no larger than a city, yet they pack the mass of several suns. Neutron stars also have incredibly strong magnetic fields and can emit powerful beams of radiation, becoming pulsars if these beams sweep across Earth. For the most massive stars, those whose cores exceed about 3 times the mass of the Sun, the core will collapse beyond even the neutron star phase, forming a black hole. Black holes are objects of such immense density that their gravitational pull is so strong, not even light can escape. The boundary around a black hole is called the event horizon. Once something crosses this threshold, it is lost to the universe forever. Black holes are among the most mysterious and extreme objects in the cosmos, and they play a pivotal role in shaping the galaxies and the space around them. The life cycle of a star, from birth in a nebula to death as a white dwarf, neutron star, or black hole, is a process that drives the evolution of galaxies and the creation of the elements necessary for life. Every atom in your body was forged in the heart of a star, scattered across space by supernovae, and eventually incorporated into new stars and planets. In this way, the story of stars is also the story of us, a reminder that we are part of the universe's ongoing cycle of creation and destruction. Stars, in their grand arc from formation to destruction, illuminate the cosmos both literally and figuratively. They are the engines of creation, the forges where the universe's most essential elements are crafted, and in their deaths, they give back to the cosmos the materials needed to spark new generations of stars, planets, and perhaps life itself. Black holes, the abyss of the cosmos. Black holes are among the most enigmatic and fascinating objects in the universe, challenging our understanding of space, time, and the very nature of reality itself. These cosmic behemoths are regions where gravity is so intense that not even light, the fastest thing in the universe, can escape. Their existence pushes the boundaries of physics to their limits, presenting us with paradoxes and mysteries that continue to perplex scientists. Yet, for all their strangeness, black holes play a crucial role in the dynamics of galaxies and the cosmos at large, making them not just oddities, but essential players in the cosmic story. Black holes come in several varieties, each with distinct origins and scales. The most common type is the stellar black hole, which forms from the gravitational collapse of a massive star at the end of its life cycle. When a star exhausts its nuclear fuel, it can no longer support itself against the relentless inward pull of gravity. If the star is massive enough, this collapse results in the formation of a black hole, a point where matter is compressed to an incredibly small volume, creating a gravitational field so strong that not even photons, the particles of light, can escape. Another, even more massive class of black holes are the supermassive black holes that reside in the centers of most galaxies, including our own Milky Way. These black holes contain millions to billions of times the mass of the Sun, and their origins are still a subject of intense scientific debate. How did these cosmic monsters form, and why are they present at the core of nearly every large galaxy? Some theories suggest that supermassive black holes grew from smaller black holes by accreting enormous amounts of gas, dust, and stars over billions of years, while others proposed that they may have formed directly in the early universe from the collapse of giant gas clouds. Regardless of their origins, supermassive black holes have profound effects on their host galaxies, influencing the orbits of stars and regulating the rate of star formation. There is also speculation about the existence of primordial black holes, hypothetical black holes that may have formed in the very early universe, long before the first stars and galaxies. These black holes could have originated from fluctuations in the density of matter shortly after the Big Bang, collapsing under their own gravity to form incredibly small, yet highly dense objects. While no primordial black holes have been definitively detected, their existence would help explain certain mysteries in cosmology, such as the nature of dark matter and the distribution of galaxies in the early universe. The most defining feature of a black hole is its event horizon, the point of no return. This boundary marks the limit beyond which nothing, not even light, can escape the gravitational pull of the black hole. Once an object crosses the event horizon, it is forever lost to the outside universe. To an outside observer, anything approaching the event horizon appears to slow down and fade, as the intense gravity warps the passage of time and stretches the light into longer wavelengths, creating what's known as gravitational redshift. However, for the object itself, there is no sense of crossing a boundary, it simply continues its fall toward the center, toward the singularity. At the very core of a black hole lies this singularity, a point where gravity becomes infinitely strong and the laws of physics as we know them break down. Here, the very fabric of space and time is warped beyond comprehension, and our current understanding of physics, including Einstein's theory of general relativity, fails to describe what happens. In the singularity, the density of matter becomes infinite, and time itself seems to cease to exist. This breakdown of physical laws is one of the great mysteries surrounding black holes, leading scientists to search for a unified theory of quantum gravity that can explain the singularity's nature. Despite their fearsome reputation as cosmic devourers, black holes are not indiscriminate vacuums, sucking in everything in their vicinity. Instead, they act more like gravitational anchors, influencing the motion of stars, gas clouds, and other objects around them. A black hole's gravitational pull is significant only near the event horizon. Objects orbiting at a safe distance are unaffected by the black hole's presence, just as planets orbit stars without being consumed. In fact, many black holes are surrounded by accretion disks, swirling rings of gas and dust that emit intense radiation as the material heats up while spiraling toward the event horizon. This radiation, especially in the case of supermassive black holes, can produce some of the brightest objects in the universe, known as quasars. Quasars are powered by material falling into supermassive black holes at the centers of galaxies, and their luminosity can outshine entire galaxies. As matter accelerates and compresses in the accretion disk around the black hole, it heats up to millions of degrees, emitting vast amounts of radiation across the electromagnetic spectrum, from X-rays to radio waves. These quasars are not only fascinating in their own right but also serve as cosmic lighthouses, allowing astronomers to study the distant universe and trace the evolution of galaxies over billions of years. Black holes, particularly the supermassive ones, also play a vital role in shaping the galaxies around them. They help regulate the formation of new stars by heating up or expelling the gas that would otherwise collapse to form new stellar nurseries. This feedback process, known as black hole feedback, prevents galaxies from becoming too massive too quickly and helps maintain the balance of star formation. Without this regulation, galaxies could grow much larger, but with fewer stars forming, which would significantly alter the universe's structure as we observe it today. One of the most mind-bending aspects of black holes is the way they warp not just space but time itself. According to Einstein's theory of general relativity, time flows more slowly in stronger gravitational fields, a phenomenon known as time dilation. Near a black hole, time slows down dramatically. For an outside observer watching someone fall into a black hole, it would seem as though time for the falling person slows to a crawl as they approach the event horizon, effectively freezing them in time. However, for the person falling in, time would appear to flow normally, and they would continue falling toward the singularity, unaware of the bizarre time effects taking place outside the event horizon. While we cannot directly observe what happens inside a black hole, its existence and effects are detectable. The gravitational waves emitted by black hole mergers, ripples in the fabric of spacetime predicted by Einstein, were detected for the first time in 2015 by the LIGO Observatory. These waves confirmed the existence of black holes and gave us a new way to observe the universe, opening a completely new field of gravitational wave astronomy. Such detections allow us to listen to black holes colliding, providing crucial insights into their properties and the nature of gravity itself. The study of black holes continues to push the boundaries of science, forcing us to rethink our understanding of space, time, and the fundamental nature of the universe. They represent the ultimate extremes of physics, where the known laws of nature break down, and where new and profound discoveries await. Yet, for all their mysteries, black holes are not just cosmic anomalies, they are vital to the story of the universe, influencing the formation of galaxies, the behavior of stars, and even the evolution of space and time itself. As we continue to explore and learn more about black holes, we move closer to unlocking the secrets of the universe's most perplexing and powerful phenomena. These abysses of the cosmos offer both terrifying and awe-inspiring glimpses into the fundamental workings of the universe, reminding us that while we have come far in our understanding, there is still so much more to uncover. Dark matter and dark energy, the invisible forces. Despite the remarkable progress we've made in understanding the cosmos, much of the universe remains hidden from our direct observation. About 85% of the matter in the universe is composed of what we call dark matter, an elusive substance that neither emits nor absorbs light and is therefore invisible to telescopes. Unlike ordinary matter, made up of protons, neutrons, and electrons, dark matter doesn't interact with electromagnetic forces, meaning it doesn't produce light, radio waves, or any other form of radiation that we can detect. Yet, its gravitational effects are unmistakable and profound, shaping the universe on the grandest of scales. Without dark matter, galaxies as we know them would not exist. The stars within galaxies, including our own Milky Way, move far too quickly for the visible matter alone to account for the gravitational force needed to keep them bound together. In the absence of dark matter, the galaxies would simply fly apart. This realization has led scientists to conclude that a vast amount of unseen mass must be providing the gravitational glue that holds galaxies and galaxy clusters together. We can infer the presence of dark matter through its gravitational influence on visible matter, most notably through an effect known as gravitational lensing. When light from a distant object, such as a galaxy or a quasar, passes near a massive galaxy cluster, the gravitational pull of the cluster bends the light, distorting the image of the background object. This bending of light reveals the presence of much more mass than what is visible, providing compelling evidence for the existence of dark matter. In fact, gravitational lensing allows astronomers to map out the distribution of dark matter in the universe, showing that it forms an invisible scaffold around which galaxies and clusters are built. Despite these indirect observations, the true nature of dark matter remains one of the most pressing mysteries in cosmology. Scientists have proposed many candidates for what dark matter might be made of, but so far, none have been definitively confirmed. Some of the leading candidates are weakly interacting massive particles, WIMPs, which are hypothetical particles that interact with normal matter only through gravity and possibly the weak nuclear force. Another potential candidate is the axion, an incredibly light particle that could also interact only very weakly with ordinary matter. Yet, despite decades of searching, using detectors buried deep underground, as well as particle accelerators and cosmic observatories, no dark matter particle has been detected. Even more mysterious than dark matter is dark energy, a force that seems to be driving the accelerated expansion of the universe. First discovered in 1998 through observations of distant supernovae, dark energy accounts for roughly 70% of the universe's total energy content, dwarfing both ordinary matter and dark matter in importance. While dark matter exerts a gravitational pull, helping to hold galaxies together, dark energy does the opposite. It acts as a repulsive force, causing the universe to expand at an ever-increasing rate. The discovery of dark energy was a monumental surprise. For most of the 20th century, cosmologists believed that the universe's expansion, set in motion by the Big Bang, was gradually slowing down due to the gravitational attraction of all the matter within it. But the supernova observations revealed the opposite. Not only was the universe expanding, but this expansion was accelerating. Something was pushing galaxies apart at faster and faster speeds. This repulsive force, now known as dark energy, appears to be woven into the very fabric of space itself. While we understand even less about dark energy than we do about dark matter, it is intimately tied to the fate of the universe. The leading explanation for dark energy comes from a concept proposed by Albert Einstein in his theory of general relativity, the cosmological constant. According to this idea, empty space isn't truly empty, it has an inherent energy, sometimes called vacuum energy, that exerts a repulsive force on the universe. As space expands, more space is created, and with it, more dark energy, leading to an accelerating expansion. However, the exact nature of dark energy remains unknown. Some scientists speculate that it might be the manifestation of a new fundamental field, akin to the electromagnetic or gravitational fields, but unlike any we've encountered before. Others propose that our understanding of gravity might be incomplete, and that dark energy could be a sign that we need a new theory of gravity to explain the large-scale behavior of the universe. As the universe continues to expand under the influence of dark energy, galaxies are being pulled further and further apart. Over billions of years, this expansion will cause galaxies to drift beyond the reach of our telescopes, vanishing from view as they move away faster than light can travel to us. If dark energy continues to dominate, the universe may expand forever, growing colder and more desolate as stars burn out, galaxies cease to form, and the cosmos descends into a state of cold, dark emptiness. This bleak, distant future is often referred to as the Big Freeze. In this scenario, stars will eventually exhaust their nuclear fuel and fade into white dwarfs, neutron stars, or black holes. As galaxies recede from one another, no new stars will form, and the remaining stars will gradually die out. Planets, if they still exist, will drift through dark, empty space, without the warmth or light of a nearby star. Over trillions of years, even black holes will evaporate through a process known as Hawking radiation, leaving behind only a cold, featureless universe devoid of structure or energy. Another possibility is that dark energy could change over time. If dark energy becomes stronger, the universe's expansion could accelerate to the point where even atoms are torn apart in a final, catastrophic event known as the Big Rip. In this scenario, galaxies, stars, planets, and even the fabric of space-time itself would be ripped apart, ending the universe in a violent and abrupt manner. Alternatively, dark energy could weaken, allowing gravity to eventually halt the expansion and reverse it, leading to a big crunch, where the universe collapses back into a singularity, potentially sparking a new Big Bang. These are only some of the possible futures of the universe, and our understanding of dark energy will be key to determining which of these scenarios will come to pass. As we continue to probe the mysteries of dark matter and dark energy, we are reminded that much of the universe remains beyond our grasp, hidden in the invisible forces that shape its destiny. For all the progress we have made in observing the cosmos, dark matter and dark energy are profound reminders of how much we have yet to discover. Together, they constitute over 95% of the universe's total mass energy content, leaving the ordinary matter, the stars, planets, and galaxies that we can see, making up only a tiny fraction of the cosmic picture. As we look deeper into the universe and develop new technologies to study its most elusive components, we may one day unlock the secrets of these invisible forces, revolutionizing our understanding of the cosmos and our place within it. The search for extraterrestrial life. One of the most tantalizing questions humanity faces is whether we are alone in the universe. Given the vast number of stars in our galaxy alone, hundreds of billions, each potentially hosting planets, it seems improbable that Earth is the only place where life has arisen. Yet, despite decades of searching, we have found no definitive evidence of extraterrestrial life. The question looms large, shaping our understanding of life itself and fueling our quest to comprehend our place in the cosmos. The search for life beyond Earth has evolved dramatically in recent decades, driven by advances in technology and an expanding understanding of the conditions necessary for life. From the pioneering efforts of the SETI, Search for Extraterrestrial Intelligence, project in the 1960s to cutting-edge astrobiology missions today, the pursuit of alien life takes many forms. SETI, in its early days, involved scanning the skies for radio signals, artificial communications that could indicate the presence of intelligent civilizations. The idea behind SETI was simple yet profound: if other intelligent beings exist, they might, like us, use technology to communicate across the vast distances of space. By listening for these signals, we hope to catch a glimpse of a distant, technologically advanced civilization. While SETI has yet to yield conclusive results, it remains an active area of research, with projects continuously scanning the skies for faint whispers from the stars. The Fermi paradox, named after physicist Enrico Fermi, underscores the dilemma: given the sheer number of stars and planets, why haven't we detected any signs of extraterrestrial civilizations? Are they simply too far away? Or is intelligent life exceedingly rare, and we are, perhaps, one of the few, or the only, species in the galaxy capable of technological communication? Meanwhile, the search for microbial life, the simplest forms of life, takes place closer to home. Astrobiologists study the conditions on other planets and moons in our solar system, seeking the chemical signatures of life. This search is largely focused on planets and moons that lie in the so-called habitable zone, around their stars, the region where conditions may allow for the existence of liquid water, a key ingredient for life as we know it. Earth's liquid water is crucial to its ability to host life, so the presence of water elsewhere in the solar system is seen as a promising indicator of potential habitability. Mars, our planetary neighbor, has long been a candidate for hosting life. Although the surface of Mars today is cold, dry, and inhospitable, evidence suggests that it was once a warmer, wetter world, with rivers, lakes, and possibly even oceans. Ancient riverbeds and sedimentary formations indicate that water flowed on Mars billions of years ago. In recent years, missions such as NASA's Perseverance rover have focused on exploring regions of Mars where ancient water once existed, searching for signs of past microbial life. While no definitive evidence has been found, the tantalizing possibility remains that Mars may have harbored life in its distant past, or even that microbial life may still exist today, hidden beneath the planet's surface. Beyond Mars, several moons in our solar system have captured the imagination of astrobiologists. Some of the most promising candidates for extraterrestrial life lie not on planets, but on the icy moons of the outer solar system. Europa, one of Jupiter's moons, and Enceladus, a moon of Saturn, are particularly intriguing. Beneath their frozen crusts lie vast oceans of liquid water, heated by the gravitational forces exerted by their parent planets. These oceans, shielded from the harsh conditions of space, may provide environments similar to Earth's deep-sea hydrothermal vents, where life thrives without sunlight, relying on chemical energy instead. In 2015, NASA's Cassini spacecraft made a groundbreaking discovery when it flew through plumes of water vapor erupting from cracks in the icy surface of Enceladus. These plumes, spewing from the moon's hidden ocean, contained organic compounds, the building blocks of life. While this is not evidence of life itself, it suggests that Enceladus has the necessary ingredients for life to exist. Similar signs of potential habitability have been detected on Europa, where scientists believe the moon's subsurface ocean is in contact with a rocky seafloor, providing the conditions for life-sustaining chemical reactions. However, the search for extraterrestrial life extends far beyond our solar system. The discovery of exoplanets, planets orbiting stars outside our solar system, has opened up an entirely new frontier in the quest for life. Thanks to missions like Kepler and TESS, Transiting Exoplanet Survey Satellite, astronomers have identified thousands of exoplanets, many of which reside in their stars' habitable zones. These exoplanets, with conditions potentially suitable for liquid water, are prime targets in the search for life. One of the most intriguing of these exoplanets is Proxima Centauri b, which orbits the star Proxima Centauri, the closest star to our solar system. Proxima Centauri b lies within the habitable zone of its star, raising the tantalizing possibility that it could harbor liquid water and, perhaps, life. Though we know little about this distant world, its proximity to Earth makes it an ideal candidate for future exploration, with planned missions and telescopes aiming to study its atmosphere for signs of habitability. Yet, as we search for life on distant planets, we must also confront the possibility that extraterrestrial life might be very different from what we expect. Life on Earth is based on carbon and relies on water as a solvent, but the universe may host entirely different forms of life that defy our understanding. Alien life might be based on silicon, or it could use methane instead of water as a solvent, as some have hypothesized for Saturn's moon Titan, which has lakes of liquid methane on its surface. The biochemical possibilities for life are vast, and the universe is under no obligation to conform to our Earth-centric view of what life should be. Some scientists, including Carl Sagan, have speculated about the possibility of life forms that exist in extreme environments that we would consider inhospitable. On Earth, extremophiles, organisms that thrive in conditions of extreme heat, cold, acidity, or radiation, demonstrate that life can flourish in environments once thought impossible for biology. This has expanded our concept of the habitable zone beyond the traditional limits, suggesting that life could exist in places we have not yet considered. As our technology advances, so too does our ability to search for life. The upcoming James Webb Space Telescope, JWST, with its ability to analyze the atmospheres of distant exoplanets, may soon provide us with the first concrete evidence of life beyond Earth. By detecting chemical signatures like oxygen, methane, or other biosignatures, the JWST could offer clues to the presence of living organisms on planets orbiting distant stars. But while the discovery of microbial life would be a momentous breakthrough, the search for intelligent life remains one of the most profound questions we face. If intelligent civilizations exist elsewhere in the galaxy, why haven't we detected them? This is the core of the Fermi paradox, the apparent contradiction between the high probability of extraterrestrial civilizations and the lack of evidence for or contact with them. Some scientists suggest that we may not have been searching long enough, or that civilizations may be using communication methods beyond our current technological capabilities. Others propose more unsettling possibilities. Perhaps intelligent civilizations are rare, or self-destruct before they can achieve interstellar communication. Still, the search continues, driven by the desire to answer one of humanity's oldest questions: are we alone? If life exists elsewhere in the universe, whether it's simple microbial life or advanced civilizations, its discovery would not only revolutionize our understanding of biology but also reshape our understanding of our place in the cosmos. Whether the universe is teeming with life or we are a rare cosmic anomaly, the search itself enriches our sense of wonder, driving us to look deeper into the mysteries of the stars and the life that may yet be hidden among them. Humanity's place in the cosmos. When we gaze up at the night sky, we are often struck by the beauty and vastness of the cosmos, yet what we see is but a tiny fraction of the universe. The stars that dot the night sky, though countless to the naked eye, represent only a small portion of the galaxies, nebulae, and cosmic phenomena that populate the cosmos. Despite the seemingly infinite expanse, that small glimpse can help us answer one of the most profound questions ever posed: what is our place in the universe? We, as humans, are intricately connected to the cosmos in ways that transcend mere observation. As Carl Sagan famously said, we are made of star stuff. This simple yet profound truth speaks to the very origins of our existence. Every atom in our bodies was forged in the heart of a dying star billions of years ago. In the final moments of a massive star's life, as it exhausts its nuclear fuel and explodes in a supernova, it scatters the elements it created, carbon, oxygen, nitrogen, iron, into space. These elements, born from the intense pressures and temperatures of stellar interiors, are the building blocks of everything we know, including life itself. The iron in our blood, the calcium in our bones, the oxygen we breathe, all of it was created in the cores of ancient stars, scattered across the cosmos by supernova explosions, and eventually coalesced into new stars, planets, and, ultimately, into the molecules that form our bodies. This cosmic alchemy, where stars transmute simple hydrogen into the heavier elements essential for life, binds us to the universe in a profound way. We are not merely observers of the universe, we are participants in its ongoing story. This realization reframes our understanding of life. We are not separate from the universe, we are part of it. The universe is in us as much as we are in the universe. Every atom that constitutes our bodies has traveled across space and time, taking part in the great cosmic processes that have shaped galaxies, stars, planets, and, eventually, life itself. This intimate connection between humans and the cosmos is a reminder of both our cosmic origins and the universal processes that continue to unfold. Yet, despite this profound connection to the stars, we are but a tiny, fragile species, living on a pale blue dot orbiting an unremarkable star in the outskirts of a vast galaxy. Earth, for all its beauty and abundance, is an infinitesimally small part of the larger universe. Our Sun, a medium-sized star among billions in the Milky Way, resides far from the galactic center, in the quiet outskirts of one of the galaxy's spiral arms. The Milky Way itself is just one galaxy among hundreds of billions in the observable universe. In the grand scheme of things, we occupy a minuscule portion of the cosmic expanse. The vastness of the universe is beyond our comprehension. The distances between stars, galaxies, and clusters of galaxies are so immense that they stretch the limits of our understanding of space and time. The light we see from distant galaxies has taken millions, or even billions, of years to reach us, meaning we are looking at the universe as it existed long ago. In this sense, when we observe the cosmos, we are not just looking outward, we are looking back in time, witnessing the history of the universe unfold before us. This vastness can feel overwhelming, even humbling, and it forces us to confront the reality of our fragility. As a species, we have only existed for a fraction of cosmic time. The universe is about 13.8 billion years old, while modern humans have existed for roughly 200,000 years, a blink of an eye on the cosmic scale. Our planet, too, is fragile, susceptible to the whims of cosmic forces such as asteroid impacts, solar flares, and the distant but inevitable changes in the sun's life cycle. The universe, for all its beauty, can be an indifferent and even hostile place. Yet, despite our seemingly insignificant place in the cosmos, we are creatures of curiosity and wonder. We have always looked to the stars, seeking to understand our surroundings and our origins. We are the universe's way of knowing itself. Through science, art, and philosophy, we have built tools to explore the universe and our place within it. Over the course of human history, we have developed the capacity to look beyond our immediate surroundings, to contemplate the nature of distant stars, galaxies, and even the beginning of the universe itself. This journey of discovery is ongoing. The more we learn about the cosmos, the more we realize how much there is left to understand. Our place in the universe is not fixed, it is constantly being redefined as we expand our knowledge of the cosmos. For much of human history, we believed Earth was the center of the universe. That view shifted with the discoveries of Copernicus and Galileo, who showed that Earth orbits the Sun. Later, we came to understand that the Sun is just one star in a vast galaxy, and that our galaxy is just one among billions. Now, we stand at the precipice of even deeper questions. Are we alone in the universe? What is the fate of the cosmos? What role will humanity play in the larger story of the universe? This pursuit of knowledge and understanding reflects a deeper truth about humanity's place in the cosmos. We are not merely a product of random chance, nor are we passive observers. We are the descendants of stars, the children of the universe, capable of pondering our own existence and the nature of reality. Our ability to ask profound questions, to seek answers, and to explore the unknown is a testament to the unique role we play in the cosmic drama. In contemplating our place in the universe, we are reminded that while we may be small in the grand scheme of things, we are part of something much larger than ourselves. Every discovery we make, every new insight into the workings of the universe, is a step toward a deeper understanding of our origins, our future, and the interconnectedness of all things. We may be a small species on a small planet, but our quest for knowledge, driven by curiosity, wonder, and imagination, allows us to transcend our physical limitations. Through the lens of science, we have ventured to the farthest reaches of space, peering into the early moments of the universe, and envisioning futures we can only begin to comprehend. In this way, our place in the cosmos is not defined by our physical size or location, but by our capacity to understand, to wonder, and to explore. As we look up at the night sky, we are not just observing the stars, we are connecting with our cosmic heritage, reaffirming that we are part of a much larger story, a story that began with the birth of the universe and continues to unfold with every discovery we make, every star we study, and every question we ask. Humanity's place in the cosmos is not one of insignificance, but of profound connection, as both participants in and observers of the grand cosmic drama. The future of the universe. What lies ahead for the universe? This is one of the most profound and complex questions we face as a species. While we can trace the history of the cosmos back to its origins in the Big Bang and chart the evolution of galaxies, stars, and planets, its future remains uncertain. Will the universe continue its expansion forever, growing colder and more desolate with each passing eon? Or will cosmic forces bring everything back together, leading to a fiery collapse in what some call the Big Crunch? And beyond these possibilities, could the universe we inhabit be just one of many in a multiverse, each with its own destiny? The fate of the universe is intricately tied to the balance of forces that govern its expansion. The discovery of dark energy in the late 20th century reshaped our understanding of the universe's future. Dark energy, a mysterious force driving the accelerated expansion of space, now appears to dominate the universe, accounting for roughly 70% of its total energy content. This expansion suggests that galaxies, stars, and even galaxy clusters are being carried away from one another at increasing speeds, like leaves drifting apart on the surface of a balloon being inflated. But whether this expansion will continue indefinitely or eventually reverse depends on the nature of dark energy and its relationship with gravity, the force that pulls matter together. If dark energy remains constant or grows stronger over time, the universe may continue to expand at an ever-accelerating rate, leading to a scenario known as the Big Freeze. In this future, galaxies will move farther and farther apart, eventually receding beyond the horizon of observability, disappearing from each other's view as the distance between them grows faster than the speed of light. Stars, the engines of cosmic energy, will exhaust their nuclear fuel and die, one by one. Massive stars will explode as supernovae, leaving behind neutron stars and black holes, while smaller stars like the Sun will fade into white dwarfs, dense, cold remnants that no longer shine. As time stretches on, trillions of years into the future, stellar remnants like white dwarfs, neutron stars, and black holes will dominate the universe, while new star formation will cease entirely. Without the raw materials for new stars, galaxies will grow dark. The planets, once vibrant worlds orbiting their parent stars, will drift through space, devoid of warmth and light. Eventually, even the most resilient black holes will evaporate through a slow process known as Hawking radiation, leaving behind only the faintest traces of their existence. This cosmic graveyard, where space is vast and cold, is often referred to as the heat death of the universe, a state of maximum entropy where no organized structures remain, and energy is evenly distributed. In this future, the universe will be a dark, empty place, with no light, no warmth, and no possibility for life as we understand it. Time will stretch on infinitely, but without any meaningful change, a frozen eternity. However, some scientists propose that dark energy might not be a permanent, unchanging force. What if dark energy weakens over time? In this scenario, the gravitational pull of matter could eventually overcome the expansion of the universe. The acceleration would slow, and the universe might reach a stable equilibrium, or even begin to contract. If gravity were to dominate, it could reverse the expansion, pulling galaxies, stars, and all matter back together in a dramatic cosmic collapse known as the Big Crunch. In the Big Crunch scenario, the universe's expansion would decelerate, halt, and reverse. Over billions of years, galaxies would draw closer and closer, colliding and merging in increasingly violent interactions. As the universe contracts, temperatures would rise, and matter would be compressed into smaller and smaller volumes. Eventually, everything, the stars, planets, galaxies, and black holes, would collapse into a single point of infinite density, a singularity. This would mirror the conditions that existed at the moment of the Big Bang, raising the possibility of a cyclic universe, where the end of one universe gives birth to the next in an eternal cycle of creation, destruction, and rebirth. In this model, the universe could oscillate between Big Bangs and Big Crunches for eternity. Yet, even this vision of cosmic collapse is not the only possible fate for the universe. Some theories suggest that dark energy could grow stronger over time, leading to a far more violent end known as the Big Rip. In this scenario, the expansion of the universe doesn't just accelerate, it accelerates to the point where it tears apart not only galaxies but also stars, planets, and eventually, the very fabric of spacetime itself. As dark energy grows stronger, it would overcome the gravitational forces binding galaxies, then the forces holding stars and planets together, and finally, even the atomic forces that bind matter. In the final moments of the Big Rip, spacetime would disintegrate, and the universe would dissolve into a featureless void. These scenarios, Big Freeze, Big Crunch, and Big Rip, represent different potential futures, but all rely on assumptions about the properties of dark energy, which remains one of the greatest mysteries in cosmology. What exactly is dark energy? Is it a constant force, or does it evolve over time? Answering these questions is crucial to understanding the ultimate fate of the universe, and ongoing research in physics and astronomy aims to uncover the nature of this enigmatic force. However, there is also the possibility that the universe we observe is just one of many. The concept of the multiverse suggests that our universe, with its particular set of physical laws, constants, and dimensions, might be just one among countless other universes, each with its own unique properties. In some of these universes, the laws of physics could be radically different, gravity might be stronger or weaker, or the forces that govern matter might not exist at all. If the multiverse exists, it raises the possibility that new universes are constantly being born, even as ours approaches its end. In a multiverse scenario, the death of one universe might be a localized event, while other universes continue to exist or are being created in other dimensions or regions of spacetime. Some scientists even propose that black holes within our universe could give rise to entirely new universes, with each black hole functioning as a kind of cosmic seed for a new reality. If true, this would mean that our universe is part of a vast, interconnected web of universes, where creation and destruction are part of an ongoing, never-ending cycle. As we contemplate these different possible futures for the universe, we are reminded of the fragility and transience of our own existence. The stars we see in the night sky, the galaxies we observe through telescopes, and even the atoms that make up our bodies are all part of a cosmic process that stretches across time and space. Our universe, vast and seemingly eternal to us, is itself a dynamic and evolving entity, subject to forces that may one day bring about its end. In pondering the future of the universe, we are also forced to consider our own place within it. What role, if any, will humanity play in the unfolding cosmic story? Will we continue to explore the stars, pushing the boundaries of knowledge, or will we remain confined to our small corner of the galaxy? And how will our understanding of the universe's ultimate fate shape our decisions about the future of our species? While the distant future of the universe may seem abstract and far removed from our daily lives, it serves as a powerful reminder of the scale and mystery of the cosmos. Whether the universe ends in a slow freeze, a fiery collapse, or a dramatic rip, its fate is intertwined with the same forces that govern the birth of stars, the formation of galaxies, and the emergence of life. The more we learn about the universe, the more we realize how much we still don't know, and the more awe-inspiring and humbling our place within it becomes. As we continue to explore the cosmos, both scientifically and philosophically, we are engaged in a journey of discovery that stretches across billions of years and trillions of miles. The future of the universe may be uncertain, but one thing is clear: the story of the cosmos is far from over, and we are fortunate to be a part of it. Conclusion: a cosmic journey in our place within it. The universe, in all its vastness and complexity, invites us to ponder questions that stretch the limits of our imagination. Where did it all begin? What is our place in this grand cosmic story? And what does the future hold for the stars, galaxies, and distant worlds that populate the night sky? From the mysteries of dark matter and dark energy to the quest for life beyond Earth, we find ourselves standing on the threshold of discovery. Every new insight into the workings of the cosmos brings us closer to understanding not just the universe, but ourselves. As we continue this journey, we are reminded that we are part of something far greater than our individual lives, a tapestry of existence woven from the very fabric of space and time. Our curiosity, our drive to explore, and our desire to learn are what connect us to the stars. We are the universe contemplating itself, driven by the same forces that birth galaxies and ignited stars. But this journey doesn't end here. It continues through the questions we ask, the discoveries we seek, and the conversations we engage in. Together, we can explore the wonders of the cosmos, delve into the mysteries of space, and imagine the boundless possibilities of the future. Join the cosmic conversation on my YouTube channel. Thank you for being part of this cosmic exploration. If you've enjoyed this journey through the universe, I invite you to continue the adventure by subscribing to my YouTube channel. By subscribing, you'll stay updated with more in-depth content on space, the universe, and the latest discoveries in astronomy. Together, we can explore topics like the origins of the cosmos, the search for alien life, black holes, and the future of space exploration. Don't forget to like, comment, and share your thoughts in the comments section. Your engagement helps keep the conversation alive and brings us closer as a community of space enthusiasts. Let me know what topics you're most curious about, and I'll cover them in future videos. Together, let's unravel the mysteries of the universe, one video at a time. Thank you for being part of this cosmic journey. The universe is waiting for us to explore it.